join me in my LinkedIn profile. So if you go to the LinkedIn, you can search for Edson Bortoni, and you can find me, and you can ask me to connect with you. I have a big network on of about 25,000 people, and every day I share news about renewable generation and energy storage systems. Of course, I am interested also in electrical machines, and nowadays we use that on electrical vehicles. So this kind of news I used to share every day. So you can go to the LinkedIn, go to the LinkedIn and ask me, look for me, Edson Bortoni, and connect to myself there. So let's go here. Today we have 2 hours of speaking here. We trying 2 hours to give a general view on renewable power generation and energy storage systems. Of course, each one of the subjects is very deep, and we can go further in each one. But we start with the introduction. Uh, we will talk about power thermal cycles and their applications to renewable generation. We are going to the thermal uh, uh, solar photovoltaics, wind generation, energy from the ocean, hydropower, and finally, energy storage systems. Uh, just here in the introduction, I would like to understand well what is alternative energy, clean energy, green energy, and renewable energy. That are terms we often read and listen about renewable generation. Alternative energy, this term started to begin to be spread in 1973, 1973 with the oil shock, the creation of the OPEP, joined with countries that produce petroleum, and the prices started to increase. So the countries started a job to look for alternatives to the oil in order to have better price. So alternative energy means alternative to fossil energy. Clean energy is that kind of energy that contribute to the cleanness of the air, of the soil, and of the water. So, for example, despite nuclear power generation is not is alternative energy because it's alternative to the oil. Well, we have the nuclear waste that dirt, the water, air, and the soil. So it's not a clean energy at all, but it is alternative energy. Green energy, that kind of energy that comes from natural resources. So wind, solar, hydro are green energy. That's interesting to note that big hydropower plants may be considered as maybe not a clean energy because of the large reservoirs that trap some vegetation before fill it up. When filling up. So along the lifespan of the hydropower plant, those vegetation can degrade and goes up to the water and to the air, releasing greenhouse gases. So it's not clean. But small power plants may be called green energy, clean energy. And of course, both are green energy. And renewable energy is that kind of energy that recyclates itself by nature. We call renewable energy that kind of energy that recyclates itself. That's not what happens, for example, nuclear. Nuclear material cannot be recycled. So that's some definition, very important definitions we have. Stay clear here. This picture shows it spans about 200 years, and we can see the consumption of energy of the society. So the consumption of energy increased a lot. Uh, since the exponential increasing. During long time, they used the biomass, coal, oil, but natural gas and other renewable energy, clean energy, are increasing their use, trying to reduce the contribution of fossil components. Here we have the same graph spanning only about 40 years. Here we have a percentage view. For example, the oil 1965 was responsible for about 40% of the total consumption, but nowadays it's about 35%. It's reducing. Coal was about 40%, and today it's about 25%. It's reducing a lot the use of coal, and the other you can see the other sources who were responsible for only 20%, and nowadays they are responsible for 4%. So they are increasing. It's very well. Talking about electricity, uh, uh, along the total consumption, 72%, almost 73% are come from non-renewable sources, and only 27.3% comes from renewable sources. And this 27.3 can be divided in hydropower, which accounts of the great majority, wind power 5.9%, solar photovoltaics, biopower, and geothermal. CSP. CSP stands for concentrating solar power and ocean power. This data is from 2020. What have seen in 2020? Let's see here, but this picture shows the importance of renewable energy demands. For example, uh, in United States, the oil company Exxon has almost the same value of a renewable company next year. In Italy, for example, the company Eni for long observe here is 2009, 2020 expectations, 2020. So Enel, which is a company that invests a lot in renewable energy, they for a long time have surpassed the Eni value, sent $103 billion against 37 billion. Iberdrola and Repsol are companies from Spain, and Iberdrola has a lot of wind energy, surpassed the Repsol for long. So, and in UK, you have the company Ørsted that invests in renewable energy, and the company British Petroleum that invests in oil. So they have almost the same value, but Ørsted is on the increasing, while British Petroleum is reducing its value. So really, renewable energy is very important now, and must increase and may increase its value. Talking about value, renewable power generation is very welcome also because of the local value creation. It means jobs creation. So we have in the world about 11.5 million people working in renewable energy here in Brazil, United States, Africa, and Europe and Asia. So with these, that is very important to create jobs, and that's what renewable energy is also contributing. So we have here a picture of people working solar photovoltaics, wind generation, offshore wind, hydropower. Um, in general, the renewable sources are compared using the LCOE, that stands for levelized the cost of energy. For sure, there are many ways to compare sources of renewable energy, but the LCOE is an index that has been used worldwide. So what means LCOE? LCOE is the result of a computation. So here in the numerator of this, you have estimation of costs from n equal to 0 to the lifespan of the alternative you are evaluating. So you have here the cost, but the cost is the summation of all the costs of that assets, investment costs, and maintenance and operation costs. Mm, you can put every cost here, and here one plus the discount rate. Here is the cost of the money, how much it costs. It can be also a calculation from the cost of money in the banks. You can use here the interest rate of the investors, or you can use the debut. WACC, which means an average value of the cost of the money, as it's written. By the way, this presentation has been recorded. You can ask the record at the end of the presentation. Here, in the denominator, you have all the energy that the alternative generates. So you have in the numerator all the costs left to the present value and all the energy that was generated by the assets. So you can calculate LCOV. Here is, I can show you a comparison of you will have a comparison of the energy cost of the several renewable and conventional power generation. You can see here residential, solar, C&I stands for commercial and industrial application of photovoltaics. Community photovoltaics is a business model that has been using worldwide. You can have large or big photovoltaic plants, and people can rent some area from the total area. So many people are owns that generation, that plants, and power or generated is divided by the people in accordance to the area of. This is a community. And here the solar photovoltaic in utility scale. This name scale is very important because they make use of the scale cost. It's, you can see that the cost reduces because here is just one guy putting photovoltaics in the roof of its house. Here is the roof is a bit bigger, community is bigger, and utility is much bigger, so you can reduce the cost. Here we have solar thermal storage. The difference between solar photovoltaics and solar thermal is that solar photovoltaics makes use of the energy stored in the photon of light. So it converts the energy stored in the photon to make electricity, while thermal power makes use of the heat increase, the temperature increase due to the radiation of the sun. So this is the difference. One makes the photovoltaics make use of the photon of light, and the thermal solar makes use of heat increase. Geothermal and wind we talked here. You can see that it seems that renewable energy is very competitive to the conventional in terms of energy. By the way, this information is from Lazard. Lazard is a consulting company. You can look for this company in the internet, Lazard, and those data is from 2019. It is very new because the data from 2020 were not released. So here you have the levelized the cost in terms of dollars per megawatt hour. Here we have the capital cost. The capital cost is the cost of installing a power plant. It's dollar per kilowatt or dollar per megawatt. So you have here the renewable energy and the conventional energy. So renewable energy is much better than other sources. Of course, it's competitive to the gas peaking and gas combined cycle. So if you look coal or nuclear, it's better, much better. Here we have the cost of the energy, a view of how it's reducing a long time. Here we have 2010 and 2019. So the cost of energy is reducing. Here is an average, the average value, but it can vary from the minimum and to the maximum. So we have here an average value. It is 0.076 dollar per kilowatt hour, or you can say $76 per megawatt hour. So you can see that geothermal is increasing. Also, hydro is increasing because the hydro alternatives are reducing worldwide. You can see the solar is reducing in dots from $378 per megawatt hour to $68 per megawatt hour. And here is the concentrating solar power. Wind offshore and wind onshore are both decreasing over time. And here we have the shadow of the conventional cost of fossil power plants. So all, all the renewables have competitive with conventional power generation. Now we are going to start with the power thermal cycles, the Rankine cycle. The Rankine cycle, the main, the fluid we have here in this cycle is the water. So let's take, for example, the point number one. We have water here at low pressure and at low temperature. We are exactly here, low pressure and low temperature. Point one. So you give pressure to the water. You pass the water by a pump. So it goes to the point two. The temperature seems to see almost the same, but the pressure increases a lot because we have here a pump. So the pressure goes to the point two. So you give heat to the fluid. You increase its temperature because you give heat, no matter where this heat comes from. We are talking here about only you give heat to the water. So the temperature increases and the pressure seems to be the same because we haven't a change of pressure here. So you go to the point three, and then you pass by a steam turbine. The steam turbine takes energy from the water that in this point is the steam. The water changed his status from liquid to gas, so the water is steam here, and you can pass by a steam turbine, and convert this energy in the steam to this mechanical energy available in the shaft. So you go to the point four because you use the pressure and almost at the same temperature. So you pass by a condenser with is a heat exchanger. So you exchange heat with the nature and water in the liquid status, for example. And we are back to the point one. So this is the Rankine cycle that you may have in mind that what the food here is water. So I said that no, you give heat to the water, doesn't matter where it comes from. It can the heat source can be nuclear, for example, when you break the atom, it releases heat, so you can use that heat. So the nuclear power plant uses this Rankine cycle. Only the fuel is nuclear, and fossil you can burn gas, oil, or coal to have to give heat here to the water. You can use, for example, sugar cane bagasse to heat. You can burn the bagasse and heat the boiler. You can use the geothermal energy. You can use biomass, either biomass in nature or you can make gasification of biomass and solar. Doesn't matter where the heat comes from. As long as you have heat here, you can have the Rankine cycle. And the power, it's important to note that the power you can get from this Rankine cycle is the flow mass. So you have because you can have a volumetric flow, which means a volume and over time. You can have liters over seconds. You can have cubic meters from hour, divided by hour. So you have a volume over time. So you have the volumetric flow. But here we are talking about mass flow. You may say kilograms per second. You can say tons or tonnelite per hour. So you have here mass flow. This delta H is the difference of enthalpy of the water here in the point 3 and the water here in the point 4. You have a difference of enthalpy. The enthalpy depends on the pressure and on the temperature, so you can calculate the enthalpy and the efficiency of the turbine. So that is the power you can have here in the shaft. Mass flow times the enthalpy variation and the efficiency of the turbine. In addition, we have the Brayton cycle. The Brayton cycle, instead of water in the cycle, you use gas in the cycle. When you say that a gas turbine, it means that gas passed by the turbine instead of water in there as a steam. So you have gas. For example, where? Air, you can have here there. So let's begin in the point one, low pressure and low temperature. You pass by a compressor instead of a pump in there, as we had in the Rankine cycle. As long as we are working with the gas, we have a compressor here, so you increase the pressure, maintaining almost to maintain this temperature. You have this heater. You have energy came from somewhere here, and then you go to the point 2 to the point 3, and then you pass by a gas turbine. So you come to the point 4, and then a heat exchanger come back to the point 1. So this is the Brighton cycle. We can use renewable mainly here to compress the air, and as we will see later. It's important to note that to compress air here, you waste about 15% of the energy you generate here. So if you generate 100% here, 15% goes to the compressor. So you have only 85% to the power plant. So I said here in this ranking cycle, I said that doesn't matter from where it comes the heat. So we have here the sugar cane. The sugar cane is a fantastic vegetal because it has very long leaves, with that covers a big area, so you can get energy from the sun for the photosynthesis. You have very long roots, so the vegetal can go down in the earth. You can go down in the earth to get energy from the earth, and you have here plant with the liquid with the sauce juice. That juice of the plant has a lot of energy. You can make sugar, you can make alcohol, can make a lot of products from this juice. And also you have here a bags. After taking the juice from the plant, you have the bags, and the bags can be used to be burnt and to have the heat we need to run the ranking cycle. So have here the sugar cane and bags. Heat burn to give the heat to the boiler. So an example here, we have a plant, sugar cane plant. So have a plantation of sugar around this facility, and you have here a lot of bags as a powder here running the facility. Here you have, you can compare this height with the height of human. So it's very interesting. Another source of bioenergy is the algae from the ocean. We are studying algae. It's very important too. And we can use wood, we can use rice, wasted wood, and so forth. Many ways to give this heat. The costs, the LCOE, as we said before, for bagasse is about $2,000 or maybe $1,000 to $2,000 per kilowatt in China, in Europe, and India, North America, rest of the world is about $1,500 per kilowatt. This is the cost of installation. Landfill gas, other wastes, vegetal waste here. Oh, what happened here? Can you see me there?
Yes, sure, we can see you.
Screen, I don't know. Something happened here. Can you see my screen there?
Yeah, you can see the
Okay,
screen.
thank
I
you,
can
thank
see.
you. Let's go. Okay, let's go. Let's continue here. Here you have other vegetables, rice, husks, and wood waste, and the renewable municipal waste. So you can see here. So by the way, this information is from the IRENA. Is a international renewable agency. The headquarters are in Germany, but it's run by Arabia, Saudi Arabia money. People that get money from the oil, they are looking to the future and seeing that renewable energy is coming. So they are investing a lot of money in this arena. You can look for the internet for arena, type arena in the Google, and you have this web page with a lot of information on renewable energy there. It's very important, very. Let's see about geothermal. Now we are using the heat from geothermal. So geothermal is it comes from the movement of the tectonic plates, creating what we call ring of fire. The place where we have earthquakes, where we have volcans, unfortunately, or it's a blast. We don't have that here in Brazil. Maybe in this part of Africa you don't have, but there is a part of Africa that has tectonic plates, and heat can be get from this ring of fire. So what they do is injecting water down there in the earth about 2,000 kilometers, or no, 2 kilometers, 2,000 meters. You you inject the water here. The water you find slice with high temperature. So the water turns into steam, goes up there. So, but here we have to clean up this this steam, because it comes with a lot of dirt from down the earth, mainly sulfur. But you can make fertilizer from that, and the steam go to the power station. So you have here the Rankine cycle. Huh? The geothermal. You have some geothermal plants around the world. So the cost of geothermal is about in 2019 about $4,000 per kilowatt. It's a very expensive when compared, for example, $2,000 per kilowatt of hydroelectric. The energy is about $73 per megawatt hour. And this is the capacity factor. What is the capacity factor, or sometimes called the plant factor? Is the result of calculation. Is the energy you generated, is the energy you generate over the energy you could generate because of the power plant you have if it worked 100% of time, it will generate its maximum. But geothermal doesn't work 100% of time because you have to clean, you have to. But here is a high number. When you have 80% of plant factor, capacity factor, it means that you can find this plant working a lot of time. Sometimes you don't work because you don't have source. For example, let's see, for example, the solar power plant. During the night, we don't have sun, so you can't generate nothing. You don't generate, it's not because you don't have a power plant, but it's because you don't have sun. So the plant factor goes down, the capacity factor goes down, maximum 50%. You have 50% of light during the day, 50% of dark during the night. So maximum 50%. But it's much less than that, as we will see. The concentrating solar thermal power is it's make use of the temperature. So you have places in the earth with high temperature. Of course, you have places low temperature in the poles, it's about minus 75 Celsius degrees, and the place is very hot, 50 degrees Celsius here in the desert, in the Saudi Arabia, India, and so forth. It's very hot. So here you see the Africa, very hot here, range here, hot here also. So you can make use of the heat created by the sun radiation of the sun rays to give heat to the boiler. We have some alternatives, these parabolic concentrators. So you have the sun rays here, and the sun rays converge to this line. So you take water at low temperature here. You have water in high temperature on the other side. This is a scan of how it works. The parabola works like that. We consider that the sun rays comes in parallel lines. The sun rays comes in parallel lines. When it hits the walls of the parabola, the ray comes to a point we call focus of the parabola. So you have the rays coming here and going to the focus of the parabola. So you have a high temperature here. You can use that. Here we have storage. We'll talk later. And the ranking cycle here. Some applications worldwide, big power plants, 50 megawatts in Spain. The energy storage here of about 7.5 full load energy storage. We have the linear Fresnel. The linear Fresnel works almost the same. So instead of having a parabola here, you have meters here converging the rays to the focus single point here. So we have parallel rays and the meters pointing to a single point. So you have here also the ranking cycle. There are some applications, technology. Heliostats, you have also meters point to a single point. So this point is very hot because of the meters pointing to that. So you can take water here at low temperature after passing by this point, have water in very high temperature, so you can go to the Rankine cycle. There are some examples. This is me, and I was in Israel. They have a plant there. So this picture was taken from the road. I was driving there, and I stopped my car and took this picture. Yeah, all the mirrors point to this single point. And this parabolic disc, the parabolic disc, it's a little bit different because here in the focus we have a Stirling motor. The Stirling motor is a motor of external combustion. You can look for, let me write here, just make sure what Stirling to for you. Stop the okay, finally. Stirling motor. The Stirling motor is a motor of external combustion. So this doesn't matter from where the energy comes, it worked very well. So the Stirling motor has been applied in countries. Here in my university, we have a lab of concentrating power. And the cost is about almost $6,000 per kilowatt hour. The energy is about 182, but it varies a lot depending on the site. And the plant factor is almost 50%. As I said, during the day we have sun, and during the night we do not have, so we can't generate unless we have energy storage. So but the capacity factor is very high. Maximum is 50%. We are reaching for 5%, which is very good. Photovoltaic, as I said before, takes energy from the photon. instead of the heat. By the way, the heat is a problem. The heat reduces the efficiency of the photovoltaics because it takes energy from the photon, not from the heat. This is a very interesting map. If you can look for this site, global solar atlas.info. You can look for this global solar atlas.info, and you have this kind of map. For example, here let's look for in the Kenya. Don't know where are you in the Kenya? Nairobi, for example. You here, the global horizontal radiation is about almost 2,000 kilowatt hour per square meter. So if you install here photovoltaics, you will get an average generation, sometimes more than that, sometimes less than that, but in the average, you have almost 2,000 kilowatt hour per square meter. So this website is very interesting. You can make some projects here. I don't use this very much, but you can make a project here. Okay? Can open details. Kitwi, are you familiar with that? So you have information. You can you can for places here, Nairobi. And okay, here, Nairobi. Oh, this is, you have this global radiation. You can put solar in your university. Let's see here. So if there is a lab there, but you can generate 150,000 megawatt hour per year. Okay, it's a very good source of information from the World Bank to other contributors. Okay, let's come back here. You have many technologies of solar cells. Have many technologies of solar cells. And there are many available technologies. We will talk. There are those hybrid solar panels. The hybrid is that you can get heat at the same time get energy from the photons. That's why it is hybrid. You have the multi-junction because you know the light that comes from the sun is rich in wavelength. That's how is the wavelength distribution of the at the top of the atmosphere, and at the sea level we have this red line. There are some reductions because of the atmosphere of water, clouds, and you can. So the solar cells works better in a wavelength than the other wavelength. So you can put solar cells that work very well here in this wavelength from 500 to 750 nanometers. You can put cells that work well here in about 1,250 nanometers, and you can put solar cells working very well here in the between 1,500 and 1,750 nanometers. So that's where you have multi-junction. Each junction working well in a given area. This area, this area, and this area, for example. So you can take profit from the light of sun in several wavelengths instead of only one if you have only one. Here it is this concentrating photovoltaics. You have a Fresnel lens here that concentrates solar radiation to a single point. Here we have details of the IV curves. Here you have the maximum current, that means the voltage when it's open. Okay. Here, when it is open circuit voltage and zero current because it's open, and the short circuit current, the voltage is zero because it's short circuited, and you have here maximum current. So this is the curve, the blue curve, IV. You can get the PV curve, which means current times voltage. You have the PV current, you have the maximum power you can extract from this panel. So you can every time look for the maximum power. That's why the MPPT does is looking for the maximum power point tracking. So always here. The influence of temperature, the temperature tries to reduce the short circuit current, and also the temperature, the increase of the temperature tries to reduce the open circuit voltage. So the temperature is an enemy from the solar panel and solar cells. This is a work we, some students here, it was published in the journal Solar Energy. You can put the solar cells in series to achieve a given voltage. You can put the solar cells in parallel to achieve a given current. So we have a race of solar cells. The potential evaluation of solar cells you can have here. As we are engineers, we have to know how to calculate the things. So the power you can extract from a solar panel is the GHI. That means global horizontal irradiation that you can take from this website. For example, you have the G8I here, global or horizontal radiation, times the area, the covered area, the area you are using, the efficiency, the rated, the nominal, the rated efficiency of the panel, times a factor of efficiency. Because this efficiency is obtained at 25 Celsius degrees. So if you work with a temperature higher than 25 degrees, so your efficiency will reduce. If you work with a temperature lower than 25 degrees, your efficiency will increase. The rate of variation is about 0.5%. It means that there is a variation in the efficiency of 0.5% at for each degree. 0.5%. For example, if you work at 40 degrees, so 40 times 25, 15, so times 0.5%, that's what you reduce your efficiency in the plant. General, this is a thermal view. It's very hot. Here is a graph of obtained from NRL. NRL stands for National Renewable Energy Laboratory from the United States. So you can look for NRL in the web and internet. If you type NRL chart, you can have this one. And we have the efficiency of the solar cells, the several solar cells that exist, from 12% to almost 50%. This is the range of variation from 12 to 50. Let's see, for example, this kind of cell is denoted by a square and a dot inside. Purple square with a dot inside. What means here in the a purple square is a dot with a dot inside? It's a 4-junction with concentrator, a high efficiency cell. There are 4 junctions. It means that it takes 4 wavelengths of the light of the sun, and with a concentrator, so you get the radiation in an area and covers it to a single point with a Fresnel lens. It's a very high efficiency cell. Oh. On the other side, we have this cell with the lowest efficiency is a red circle, a dye sensitized cell, very low efficiency. But what we have in the market is about 70%. 70% is a filled circle, red filled circle. It's organic cell, various types of organic cells. We are here in the market. 70%. Okay. This I will not enter in this. This is a project from Google. You can type project sunroof. You can get this in the Google. Okay. This is a calculator from NRL. The software, it's available in the internet. PV watts. I can go here, type here, can go to the website pvwatts.nrel.gov. You can go here. Let's make a calculation here. Let's see my city, Itajubá, Gerais, Brazil. Let's see. Oh, it's fine. Itajubá, Minas Gerais, Brazil. Latitude, longitude. Is this place here, Itajubá, the map. So let's go. Make the calculation. Let's see the area. I click here. So I can look for my university. Versus a very nice city. Okay. Here is the I right now I am here. Exactly here. Right now I'm here. But I used it to work here in the Center of Excellence in Energy Efficiency. You can let's put solar panels in this area. So I click here, 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 there. So let's put solar panel in that place. Save. So residential, let's see, let's say commercial. Price of the energy. Let's go. Voila. I can generate 155,000 kilowatt hour per year. You can have the information along the year, and it saves me some money, $31,000. So if I invest there in solar panels, I will get $31,000 back. This is a zooming of the results. Okay, let's go back. The right inclination is very important because if you are in the important thing is to have uh, the sun rays orthogonal with the normal with the plate. So it varies along their position. If you are here, the solar plates may stay at 90 degrees, and if you are exactly here, the solar plates may be at to the horizontal 0 degrees. But as we have this, important to note that we have this rotation axis, the north, along the months. We have changing of angle of the Earth. See, Africa is here. And we have tracking mountains that we can get 30% more of energy using tracking mountains. 30%. So you can have something like this, looking for this is one axis, and the two axes. The second axis you can move looking for the sun. This is a two-axis tracking mountain. Can move in this direction, can move in the other direction. This is a 2x mountain. So we have some field projects, very interesting. This is the Chile desert. Chile desert is very high and that low temperature, so it's a dry place. It's very important. It's very nice to have solar generation there. Some examples in China. China, they are installing many solar panels. You can mount on the roofs. Commercial places. You can use it floating over the lakes. You can put with many advantages. For example, you reduce the temperature of the cell. You can reduce the evaporation of the water. Some dirt will reduce. Huh? Very interesting. Over channels, areas already used with no use for the humankind. You can put solar panels there. Parking lots. You can make inks. You can flexible. You can use in windows and make a lot of experiments with transparent solar cells. Can use that in these buildings. Of course, people from designers can brand. The problem of cleaning. Right now, there is a study of cleaning. What does a what does what is the reduction of generation because of dirt? So you can use automatic cleaning. Cleaning in many ways, robot cleaning. You can put animals to feed and to clean, but sometimes the animals can go and create over the plates, creating cracks. So that's what propaganda of automatic. Some hazards, sometimes it happens, burn of short circuits in the panels, rains, very heavy rains with ice, stones, hurricanes, rains. The costs of photovoltaics are reducing a lot. It's very important. So if you are using this trend, you could find here in 2008, 2020, a very small cost. But it seems that is a other trend here. So it's reducing much more here, about less than about $0.2 per watt, $2,000 per kilowatt. So the cost is reducing. 2019, it was less than $1,000 per kilowatt. This is the cost of the cell, but there are many other costs, installation costs, costs that goes to that 2,000. Um, the cost of energy is reducing, and the capacity factor is about 18%. You know, as I said before, you have sun only during the day, and during the night you don't have sun, so the capacity factor is at maximum 50%. But even during the day, the sun rises in the about 6 a.m. and have it stop at the noon, and it start reducing to 6 p.m. So it's the capacity factor is not as a square here, but it's like a sinusoid. So you have less than a square, less than 50%. That's why they reach about 18%. So let's talk about wind power. Have wind power, the equation that governs the wind power generation is that the power you can get is CP is the efficiency of the wind generation at all. Rho is a Greek letter. It's the specific mass of this case of the air. It's about 1.2 kilograms per cubic meter. 1.2. A is the area covered by the crater, and the V is the wind speed, right, to the cubic power. So this is the equation. The wind generator works like that. Here we have a picture showing the power output against the wind speed. What do we see here? That's a wind. There is a wind speed that the generator doesn't work. So in this case, when we have less than 2 meters per second, it is possible to make the generator run. And as long the speed increases, the power increases at cube rate of the velocity. So the power increases too. Of course, there is a limitation of the generator. I can't generate as long as with the wind speed, because the generator in the wind generator, the generator itself must be very big. So there is a limitation of the generation. Despite you have a lot of wind, there is a limitation of generation. This limitation is achieved by reducing the efficiency of the turbine. When you reduce the efficiency of the turbine, you can control the power generated even with the highest wind speed. We, we change the efficiency of the turbine by moving the blades of the turbine, so reducing its efficiency. Okay? And there is a point where the speed of the wind is so strong, so high, that you have to cut off your turbine. You have to stop your turbine, otherwise the turbine would be damaged. So to avoid damage, you stop the turbine for strong winds. So that is how the wind turbine works. There is a minimum wind speed, so the power increase with the wind speed, and then here we stop to increase the power generated power, even the speed increases by reducing the turbine efficiency. There is a cutoff. Okay. Of course, the wind speed is increased with the height. As high you are, the wind is strong. So there are mathematical models for that. There is a statistical distribution of the wind. They used to fit with a Weibull distribution and the direction of the wind. There is also a map in the internet. You can go to the Global Wind Atlas.info and they have this. Let's look for this. You go to the internet. Let's look for Nairobi here. Nairobi Canyon. Okay? Okay. Can expand the graph here. So let's look for wind data. So here we have the power density. It's in the minimum 4 watts per square meter, maximum of 50 watts per square meter. It's a very good place. So we can look for wind speeds. This is the rows of wind. It shows that the wind goes almost to the northeast. Here is the north. Here is the east. So here is in the northeast. So the wind there goes almost to the northeast direction. Okay, very good. And you can change here the height. For example, 200 meters high. So increase to 77. Remember, this number was 40, and this number was 50. To now it's 86.8 watts per square meter. If you put a tower at 200 meters high. Okay, you can. So this is very interesting curve. I don't know. Generate plot. Here. Here you have the power I showed it to you. Very interesting. Okay, you can look for this data, this global wind atlas to evaluate the generation capacity. Land-based applications. This is a very nice picture or video. You have here, you have here this Nordex generator. They made a very nice moving. You have here, it's very interesting. You have here those motors here to move the entire, you call nacelle. We call nacelle this place where is the generator. So you can move to look for the strongest wind. You have sensors that shows you how you have to move the entire nacelle to look for the maximum wind. So these motors make this work moving the nacelle. Yeah, you have here blades here, the hub, we say the hub, and the generator, and between the hub and the generator, you have a speed multiplier. So you have here very low speed. After multiplying that, you have a high speed here. It's important you know that as high, the higher is the speed, the lower is the volume of the generator. If you want a small generator, you have to have high speeds. So that's why you have a speed amplifier here. Okay, you have so you have the blades, the hub, one shaft here. You have the speed multiplier here, another shaft, and a small generator because you have biggest speed. Go to the you can find this video at YouTube. If you type there how wind turbine works, you can find this video. Here we are inside the hub right now. Well, this is very important. We are inside of the hub right now. So we can see three motors here. This motor moves the blades to change that efficiency I told you before. So you change the efficiency by moving the blades. We call this pitch. The pitch of the blade you can adjust here. Okay. Well, that's the wind turbine. So you have here the hub, the blades, and the hub, and the speed multiplier. And you have here operator because it works at a higher speed. So we try to put the wind generators in the top of the mountains because when you are higher level, you have more speed. And base generators in the top mountains or close to the sea, borders of to the sea. So you have strong winds here. Onshore, so the price is going down about $1.4 thousand per kilowatt, and the cost of the energy is going down to about $53 per megawatt hour. The capacity factor are increasing to 35%. Well, always something can go bad. You have some hazards, can try to avoid those hazards by monitoring. It's increasing the monitoring turbines is very offshore applications in the sea. So it's not too much spread, but we have examples here in the North Sea, in the Europe, in the coast of China, and in the coast of United States, and starting the coast of Brazil. It's starting the application of very nice picture here. As you are in the sea now, you want to reduce the maintenance costs, so you take the speed amplifier from the solution. Because the speed amplifier gives a lot of maintenance. So you take out. When you take it out, you have a low speed and a bigger generator. So there is only one shaft here and a big generator. So it is a little bit different from how to fix the turbines. So when you have a less than 60-meter depth, you can use a land-based fixed bottom. When you have more than 60 meters depth, you use floaters. So you have to use floaters here. That's the difference of using fixed bottom or floaters. It depends on the depth of the floor of the ocean. Okay. Substations, in general, as long you have speed variation, you also will have at the end uh, eventually frequency variation. So there is a AC substation for uh, to merge or to connect all the wind generators at a variable frequency. So you convert this variable frequency to DC, transmits there is a transmission, a DC transmission line here, and at the land you convert the DC to AC at the frequency you want. So that's how it works. Every offshore application will have some substations here. And the costs, it's about, it is expensive, almost $4,000 per kilowatt hour. It's expensive, but the oil companies, they have experienced work in the sea. That's why the oil companies are jumping to this application of wind offshore turbines application. Now we are going to the ocean, power from the ocean. I divide in marine current, tidal, and the waves. There's a small movie here. Remember this movie when you were a child? This is Searching for Nemo. It is very interesting that the fishes are navigating or they are swimming in a ocean current. They look for ocean currents to facilitate their migration. I can say that we have rivers in the ocean. So places where you have marine currents in the ocean. So it's very interesting to have. So the marine currents are for centuries known. Navigations made use of currents until today. And there is a website that talked about these marine currents. I will go over there. So there are many ways to explore marine currents, and the equation that governs the power generation is almost the same. Is the same of the equation that is used in the wind power generation. The same equation, you have to take on the differences here. The density of the water is about 1,000 times the density of the air, while the density of the air is 1.2 kilos per cubic meter. The density of the water is 1,000 kilos per cubic meter. It's almost 1,000 greater. So you can have small areas generating the same power, the wind. So here you have marine current applications, also with the substations. Okay. And here we are going to the please turn off your microphone. So the tidal depends on the moon position because of the mass of the moon, the gravity of the moon, it makes the tidal. What's happening? There is a now. Are you there?
Yes, you can still hear me.
Okay, okay. Let's continue here then. So you have a variation of the height of the waters depending on the position of the moon. So taking this, considering this, you can have something like this. You can have gates when you have a difference of height. During the night, so you have the high tidal, so the water comes to a lake, a lagoon, and during the day, the ocean goes down, and you have a difference of height here. You can generate the energy from this height. So you can have this. Now, during the night, the water goes in a direction, and during the day, the water goes in the other direction. So you can put a turbine here and use this variation of the direction of the water. So there is a website with this data. This website is the Wind Guru, that shows mm, the titles. I will use the Wind Guru later. So you may have two turbines. One turbine works when the flux in one direction, and the other turbine can work when the flux is in the other direction. So, and finally, we can have waves. So the wave is you can model a wave like a sinusoid. So you have the peak to peak difference, the height difference, and you can have the difference, the wavelength, the length between crests. So this is the power. Eventually, this is the power of a wave. Depends on the square of the heights and the time between peaks. Time between peaks. So, okay, this is the equation. So take note of this equation, because this is the equation we can get energy from the waves. And the software available in the internet is the Wind Guru. I will click here, and I will go to the software we have made. This software, Wind Guru, yes, this is New Zealand. You have here the wave height. So in that equation, this line here is here. So 1.1 meter, 1.3, 1.2 meter, 2.5 meter. And the period T between crests. So you have the period here, 8 seconds, 14 seconds, 12 seconds, 6, 8 seconds. So all you need to calculate this equation, you have here in this website, Wind Guru. Okay? Okay. The way you can get the energy from the ocean, you can use this arm to it varies with the waves. In general, uh, you use to pressure water, uh, let's say drinking water. So you instead of salt water, drinking water, you pressurize water here, and you can use this pressurized water to generate the energy. So in general, what they do is to pressurize, so it moves with the waves and pressurize. You can do rotating mass as that to rotate with the waves. You can use a flex and bound movements of the waves. Again, you pressurize water to generate energy, movement. This is an example application. You can use buoy. Again, it pressurizes water in this point here. So you have low pressure water, a cycle here, low pressure water, and and as long you are going to pressuring water, you have a high pressure water line here, and you can use there to generate. Here as a point absorber, here we have linear generators here. So instead of having rotating generators, you have linear generators. Well, let's go. Well, we also have this hydro energy. The hydro energy, this kind of hydro energy, you have the dam here, the barrage here, the high pressure water here to a turbine energy, or you can have this deviation. Your dam is here, and you have the deviation of the water to a place, and then you have the high pressure to the water to the turbine. You can have, depending on the arrangement, you make surge thing. So the power you can get from hydro is given by this equation. The P is the power. This is the density of the water, the gravity acceleration, the flow, the height, and the efficiency of the turbine. So you have here the upstream and the downstream. So you have the height is the difference between the upstream and the downstream. You have the flow. Everything else is taken at least in um, planning season. Uh, you take it as a constant. Therefore, the difference, the variables you have is the flow and the height. You may have a micro, small, and large power plants depending on how small and high is the head and flow. So you may have small head, you may have high head. This is an example of the small head application. And this is application of high head application. So we have a big difference between the upstream and the downstream. You may have a difference in the flow. You may have a small flow or high flow. This is an example of a small flow hydropower plant. And this is an example of high flow. This is a picture from Itaipu here in Brazil, hydropower plant. This diameter is a 10 meters diameter, so a huge flow here. And you may have a difference of volume. This is a kind of no volume. This is what we call runoff river power plant because it doesn't have a reservoir. And here we have a Taipu with a big reservoir here. And then you may have a micro generation, hydro generation. Containers have mounting containers, small power plants, and the large power plants. Here we have the power plant, and here is nice because we have a pumped storage power plant here. Let's talk about that later. And here is a big, huge power plant. Madeira River. It means wood river. And the biggest hydropower plant at this moment is the Chinese hydropower plant. They call there Three Gorges power plant. It's the biggest we have nowadays. Urban, the cities. The total capacity, the first is China, Brazil, and the United States, Canada, and so forth. Here, difference of capacity. Africa has a very low capacity installed, but and a low energy in hydropower plant. Interesting that Asia has the biggest installed capacity and the biggest energy. And America has the third place of installed capacity, but in the second place, there is more. Europe fall from second to fourth place. Now the generation is about $1,700 per kilowatt. The energy is $47 per megawatt hour, and the capacity factor about 50%. So we are going to the energy storage systems. You know, energy storage systems may be applied for several applications, include power quality regulation, voltage support, and black start. But we are going to study energy storage for energy applications. And the problem is that all the power generation based on renewable resource, they are very variable. Doesn't matter. You know, the flow in a river is variable. You can see the same river can go to the drop to the flood. So it shows the variation of the flow in the river. So you have along the time a lot of variation. And the energy storage comes to reduce this variation. So you can store energy when you have a lot of energy, and you can release this energy when there is a lack of energy, trying to regulate or to reduce this variation. So you can do like that. We have mechanical ways to store energy. We can have electrochemical, we can have a thermal storage and electrical storage, and finally gas storage. Let's see the application of each one. We are talking about modules here. So modules from 1 kilowatt to modules of 1 gigawatt. And you can release or absorb power in seconds, here milliseconds, in minutes and hours and even years, in the hours. So you can have here in the area uh, supercapacitors, super magnets, energy storage, flywheels, and the batteries cover all of this area, supercapacitors, and pumped hydro, compressed air, energy storage systems, hydrogen, and synthetic natural gas. Synthetic natural gas, they call syngas, synthetic natural gas. Let's say each one. Let's see each one. When you have mechanical, you can use the gravitational energy, so the potential energy. So the energy stored in a mass is proportional to the height. So you can do like that, store energy in a upper reservoir and use that in a lower reservoir. You can act as a generator or as a motor here. So the energy stored is the proportional to the density, the gravity, the volume of this reservoir, and the number of hours we need to fill this reservoir. Here we have many applications of here. It is interesting. Take water from the ocean and make a lake of salt water. Here the river passing by here, and so you have an upper reservoir. Very interesting. Can store energy in a mass, and this is a huge cement block, so you can use electric train to go up and store energy and go down and release the energy when necessary. Spinning mass, flywheels, né? Then the energy is stored using this equation, half of inertia times the square of the speed. So you can spin this strong mass in a high speed and save energy. Of course, we will try to reduce the power, the wasted power in the bearings and in friction and ventilation using a vacuum chamber, so you can reduce those losses and increase the stored energy. Applications throughout the world. Compressed air means to use the excedent power or energy to compress air in a cavern or in cylinders, or you can use the mechanical, the excedent energy to compress air in a cavern and use this compressed air there in the, remember we have to compress air in the Brighton cycle. You can now you can get compressed air from the cavern. So you compress air to the cavern, pass by a heater, and then you can generate it. Batteries, flow batteries, and the batteries in the electrical vehicles, they have a lot of application and are based on the chemical engineering, chemical explanations that we will not see here. So you can save energy in a supercapacitor. So you can make electrolysis and charge and discharge the capacitor here. The energy stored is half of C is the capacitance, the square the V, the square the voltage. So you can save a lot of energy, mainly in high voltage capacitors. And superconductivity magnetic coils. So you can have a superconductive here, a very low temperature, using helium or nitrogen, and save store energy here in the inductor. So the energy stored is half of the value of the inductance and the square current. Thermal stored in molten salt or ice bear. Remember the CSP, we have to store energy so we can store the heat in molten salt and cold in this molten salt. The heat may be high temperature or low temperature. So in the solar power plants, concentrating power plants, you sometimes you have molten salt applications to store energy. So here we have an application of. Here is an application of ice bear. So during the night, we make a nice air, a bear, and we can use this ice bear to refrigerate during the day instead of using air conditioner systems and uh, using electrical energy. We can use the energy stored in the ice bear. Now we have the natural gas. It's the hydrogen is very important. You can do electrolysis while generating energy. That's what we call green hydrogen. What is green hydrogen? Is the hydrogen created by green sources. So we can use, for example, wind offshore energy to generate power and then make electrolysis and use this hydrogen when necessary. So it becomes a dispatchable power. So generate the energy and make a water electrolysis separating water is H2O, so we can separate the hydrogen from the oxygen and when necessary make it energetic. And the natural gas is so we can from either wind generation or solar photovoltaics make electrolysis, separating the hydrogen. You can store the hydrogen, or you can mix the hydrogen with the mm, carbon dioxide from the industry, and you can make methanization. Now you can have methane here with the hydrogen and the carbon here, the oxygen. So you have a synthetic natural gas here. You can store the natural gas, or you can use the natural gas in the industry, or in heating, or creating electricity again. So this is the future. So to make hydrogen with the renewable sources, methanization, using for industry, heating, cooling, or using as electrical. Here is the application regarding power and the energy and the time frame of each one of the batteries or the energy stored systems, and the cost, the the cost of the energy cost and the capacity cost, how it costs to construct and how it costs to maintain. So we have here, this is a paper I published recently. Okay, that's all. It takes a little bit more than 2 hours, 2 hours and 10 minutes. And I'm here to answer your questions. What do you want to know more? Renewable power generation and energy storage systems.
Uh, hello, hello.
Hello.
Thank you so much, Professor Emerson. That was a very detailed, clear, and uh, organized presentation. I also saw that Professor Shamia from Technical University of Kenya shared on that. So for those who have questions, you can unmute and ask questions for the next few minutes before we close the session. Thank you very much, sir.
Okay.
Yes, thank you, sir, and very much appreciated for the kind of talk you've given us. At least more insights for some of us who are doing research. We at least we got so much insights. Now we know at least a way forward in terms of renewable energy. So I have one question, and I just want to get your view because I've been in the field of renewable energy, and I will want you to maybe tell me more on the fate of concentrated solar power for smaller regions. And also you can also tell me about your view on sustainability of concentrated solar power with regards to destructive technologies such as AI, ML, and stuff like those. So thanks. I really appreciate it.
Yeah, it's very good. It's important that you have recorded this presentation so you can see it again. And feel free to contact me if you have further issues about the presentation or other things related to that. Again, I reinforce to look for me in the LinkedIn, so you can look it for Edson Bertoni there in, let me see, you can look for me, Edson Bertoni there in the LinkedIn. So you can contact connect with me there, and if necessary, make some questions there. Okay.
Yeah, thanks a lot.
Okay, great.
I would like to say something.
Okay, go ahead.
Yeah, my name is Professor Engineer Samir Hamir from the Technical University of Kenya. I
Okay.
firstly would like to thank you for a very well delivered presentation. I think it was well machined and annealed to perfection in the context of energy. I belong to the field of aerospace engineering. That was my background schooling in that context, and also electrical engineering and in the context of energy and energy storage systems. And I would like to drive this discussion from a collaboration standpoint, maybe to look into joint collaboration for CSP as one of the IEE young professionals had mentioned, which is very important, especially maybe an experimental test bed like the Helios, Helio 1, Helio 2, for instance, at Stellenbosch University, where you have these Helio sets, and they are experimenting the power tower concept. They have an 18-meter tower. I used to work in the labs there as a postdoctoral fellow. And I think that type of knowledge, know-how would be great to bring into, say, Technical University of Kenya with your university, Itajuba in Brazil, and looking at even bringing other universities on board, even having a molten salt storage facility, because as we all know, the smart grid and the whole constituency of the fourth industrial revolution brings into all of these elements. So that was my add-on to this in terms of collaboration. And one thing that we must all remember, that competition is a driving force, but cooperation or collaboration is an enabler. And that is what I'm trying to enable in this conversation. Thank you very much again for your good presentation.
Thank you. I'm very happy, and we are open for any kind of collaboration. We please, I will write down here my email. Okay, you can look, send a message to me so we can start this conversation. We have a very, very active international relationship department here. I sure I can put you in touch with them. As you see, I am director of the university, but I'm very interested in all of these energy matters. My vice rector is also in the aerospace area. He came from Embraer. I don't know if if you know this Brazilian company that.
Yes, I know. I know that even Kenya Airways has some of the planes for Embraer. Yes.
Okay, nice, very nice. And we can, of course, we can join our efforts because we can also use technologies used in the airspace to the to the energy systems. We can merge both uh, technologies, and we can do that here or there. We can cooperate with there. We have here in the university a lab with this concentrating solar power. We don't have here this solar tower, as you said, but we have here these parabolic concentrators. We have here these parabolic discs with Stirling motors. So sure, please send me an email so we can start this collaboration very soon. We have students from Africa here. We have in Brazil this. There are countries in Africa that speaks Portuguese, so they come to Brazil to study. But also we are in this internationalization process. We are receiving English speakers students, and we can do that. We can send the students to there too, and of course we can collaborate. It's very important. We have receiving Portuguese speakers from Africa. We are going to receive people from Nigeria speaking English, but we can extend this collaboration. I'm very happy with that.
Thank you very much.
Okay, I'm very happy to share this time with you guys, and feel free to contact me whenever you want. I appreciate very much.
Okay, thank you. Thank you. We are also very honored, Professor Emerson. Thank you for having time for us. Yeah, it was a very interesting sessions. That was all attending. My name is Chris Modemi. I'm the best day for Kenya section ambassador, and I'm very honored for who attended the sessions also. I hope you learned. So I would like, I was asking if you can share the presentation with me, Prof, so that they can share with all the members. And I also request members to register so that they can get the recording and maybe the presentation. I hope that is okay with you, if you can share the presentation.
Okay, it's a pleasure for me too to stay with you here. I hope you have recorded this meeting, don't you? Don't you record this
Yes, I
meeting?
have recorded
Yeah.
the meeting.
So you can share the records to everybody as necessary, because all of those pictures are obtained freely obtained in the internet, so the interested people can look for them. Okay.
Okay, thank you. So yeah, we are coming to the end of the
Yeah.
session. We it was very detailed indeed. So maybe I will welcome Gideji, who is the YP chair for Kenya section. Maybe can share before we close.
Okay. Thank you very much. See you guys. Bye bye.
Hello, Mujun. Uh, I see he is not in a position to do that. So thank you everyone, and it was a great afternoon. It's 5 p.m. in Kenya. Thank you, Prof,
Oh,
for the interesting
yeah.
session. We appreciate.
Okay.
So that is the end of our session today. I will look uh, for future interaction for more future interactions with you. Thank you, Asante
Yeah,
Sana.
and
See you
Chris,
in the next session.
Chris, I hope the next maybe sessions we could also organize for another session with him, because I think I enjoyed the session and really looking forward to learn from him and at least know more into the energy sector, especially that we from Kenya are now gearing towards ensuring we have a more cleaner and sustainable energy. So yeah, we're looking forward to get more conversations from you, and thanks you for attending.
Okay. Great.
Hey, Chris.
Yeah.
Hello.
Hello, I can hear. Oh, okay. Muriungi is here. So Muriungi, maybe you can say something before we close.
Yeah, I'm sorry. My internet kind of frozen at the time I was to comment. So I'm sorry for that. But I really enjoyed the session, and this is really a nice job, Chris and More University team, and all the other partners who really made this session a success. We look forward for more insightful and thorough sessions like these ones. Thank you very much.
Okay, thank you, thank you. We appreciate and we are honored for all who attended. It's an honor having you here. Asante sana, you can leave the meeting at your own pleasure.